Day 20, page 622, problem 16. Once again, you draw the diagram. This will be a vector problem. There are a couple of ways to do this problem, but the way I'm going to do it is with the electric fields. I'm looking at the spot, I'm trying to find a spot where E will be 0. The electric field strength will be 0. Now I know that, and you have to imagine here a line that goes through these 2 point charges, and the line can extend to the left or to the right. But if you look at the space between these 2 points right now, I'll draw this and maybe erase it, but there's any location in here, any location, but I'll take the middle location, doesn't really matter where. But if I pick any location between these 2, what's going to happen is if I put a charge there, well, let's say, we're going to be putting a plus charge of 2 nanocoulombs in a few minutes here, but any positive charge, even a speck of a positive test charge, that positive test charge will have a force to the right because the positive 4 is repelling it to the right and the negative 1 is attracting it to the right. So anywhere in that space between those 2 charges, the net force will be to the right. The net field will be to the right. So the answer to the problem cannot be to the right, or between these 2 charges. The location that we're looking for is way to the left of this guy over here, which also cannot be true because once you get out there to the left, let me erase that a little bit to the left. If I'm there at the left by the 4, that 4 nanocoulombs will repel or have a field to the left, but it'll be really strong because it's a large charge and you're close to it. But the negative 1 will be attracting or having a field to the right, but weak. So there's no way that those 2 force arrows can cancel because the positive 4 nanocoulomb force or field would be stronger at that location because you're closer to a larger charge. So the final answer must be somewhere to the right of the negative 1 nanocoulomb. And if you're really savvy, you can probably do this proportionally right now, but I'm just going to work it all out mathematically, erase all that. But so our location that we're looking for is over here somewhere. Bottom line is, if we look at, you can look at force or field, doesn't really matter. I'm going to just do it in terms of field because the arrows will be in the same direction. For example, both of these 2 charges, the plus 4 and the minus 1, have electric fields. The electric field for the positive 4 nanocoulomb is outward in all directions three-dimensionally, but all I care about is that it goes out from the 4 and it ends up, I'll use blue, I'm going to call this E sub 1. It's out, that's only one part of one vector of a million I could draw emanating radially outward from the plus 4 nanocoulomb. It's away from a positive source. The 4 is called the source. Once again, the plus 2 nanocoulombs is insignificant here. It doesn't really matter what our charge that we're placing out here is. Plus 2, plus 3, plus 4, plus 5. Although we don't want that charge out there to be so dominant, it's affecting the other charges, but we're ignoring that for now. The negative 1 nanocoulomb charge, however, has a field that always points in. I could draw a bunch of arrows pointing in, field vector arrows or force vector arrows, but I'm just doing fields here. But it's always towards the minus 1. Now, I'm going to call that E sub 2, based on the second charge. Now, E sub 2 can be equal to E sub 1, or even bigger, because when you're close, the field and the force goes up. But I don't want either one of those to be bigger. The principle here, or the concept here, is that I want E sub 1 to be equal to E sub 2. E sub 1 is the field from the 4 nanocoulomb charge, and if you remember, our basic point charge field equation is E equals KQ over R squared. Once again, you could do this with forces and it would work out the same way as well. But I'm doing it with electric field strength. You're going to plug in E sub 1. Now let's get a little creative or symbolize our distances here. And here's how I'll do that. This distance from the plus 4 will be, how far apart are they? Oh, they're 1 meter apart. And the key is, I'm going to call this X. How far I am to the right, I'm going to call that X. And then this is 1 meter. So my distance from the 4 nanocoulomb charge is 1 meter plus X. So E1 will be K times Q1, which is 4 nanocoulombs, 4 times 10 to the negative ninth. I'll remember to plug that in when I start the problem, although there's a little trick here you'll see. Over R squared, it's going to be 1 meter plus X meters squared equals E sub 2. Once again, we don't need to worry about any negatives here because it's all taken care of with the arrows we've drawn on our diagram. So for E2, that's going to be our electric field strength due to the negative 1 nanocoulomb charge. It's going to be K times 1, don't plug in the negative, nanocoulomb. If you want to plug in 1 times 10 to the negative ninth, you can, but you'll see a shortcut here, over X squared. All right, so you'll solve that for X. The only unknown in that equation is X. Now I have put in units there, but what you notice on both sides, that those units, or nano, will cancel out on both sides. The K will cancel out on both sides. And the other trick here is, like we did with some of the universal gravity problems, to get rid of the square, so you don't have to square a binomial. Squaring the 1 plus x is going to complicate the problem. But if I take the square root of both sides of this equation, I end up with 2, let me check that, 2, taking the square root of this side, over 1 plus x, because the square root of the quantity 1 plus x is just 1 plus x, equals, square root of 1 is 1, over x. Solve that for x. It's pretty simple, cross multiply, I'll let you do that.